Imagine a world where AI doesn't just predict the next word in a sentence, but understands the physics of a falling apple, the mechanics of a rotating gear, or the fluid dynamics of a swirling galaxy. This isn't science fiction. It's the frontier of physical world modeling in artificial intelligence, and it's changing how machines learn about reality. For decades, AI has been trained on massive datasets, images, text, audio, learning patterns through statistical correlation. But that approach has a fundamental flaw. It doesn't understand causation. It sees that when a ball is dropped, it falls. But it doesn't know why, because of gravity, because of mass, because of spacetime curvature. It just learns the pattern. Enter differentiable physics engines, simulation tools that treat physical laws as mathematical functions that can be optimized through gradients. These engines are the bridge between abstract neural networks and the real world. They allow AI to simulate how objects move, collide, deform, and interact, using equations derived from Newtonian mechanics, fluid dynamics, or even quantum principles. But here's where it gets powerful. When you integrate these physics engines with deep learning, you create systems that don't just simulate the world, they learn from it. For example, a robot arm learning to grasp a cup doesn't just memorize successful motions. It simulates the cup's shape, weight, center of mass, and the forces involved in gripping. And because the simulation is differentiable, the AI can adjust its actions based on how small changes affect the outcome, using backpropagation not just through layers of neurons, but through entire physical processes. This is called physics-informed machine learning. The neural network isn't just guessing, it's constrained by physical laws. It can't predict that a ball will float upward unless the input data violates known physics. This dramatically improves generalization, especially in scenarios where real-world data is scarce or dangerous to collect. Take autonomous vehicles. Training them solely on real-world driving footage is expensive, risky, and limited. But with a physics-aware simulator, engineers can generate millions of edge cases, slippery roads, sudden obstacles, sensor failures, without ever leaving the lab. The AI learns not just what to do, but why certain actions are safe or dangerous, grounded in real mechanics. But physics isn't always smooth. Real-world systems are chaotic. A falling leaf doesn't follow a clean parabolic path. It tumbles, twists, and dances on air currents. To model this, researchers are blending neural networks with partial differential equations, PDEs, like the Navier-Stokes equations for fluid flow. These hybrid models, known as physics-informed neural networks, PINNs, learn to approximate solutions to complex PDEs while respecting conservation laws like mass, momentum, and energy. And it's not just fluids. In materials science, AI is now simulating how cracks propagate through metal under stress, using finite element methods embedded within neural architectures. In robotics, AI learns to control soft robots, devices with no rigid parts, by simulating their continuous deformation using differential geometry and elasticity theory. Even in climate modeling, where traditional simulations are computationally prohibitive, physicists are training neural networks to emulate the behavior of massive climate systems, while being forced to obey thermodynamic constraints. The result? Faster, more accurate projections of global warming, extreme weather, and sea level rise. But the real breakthrough lies in inverse problems. Instead of simulating the future from known initial conditions, AI can now work backward. Given a sequence of observations, say a video of a collapsing bridge, it can infer unknown parameters, the material strength, the load distribution, even hidden structural flaws. This is transformational for diagnostics in infrastructure, aerospace, and medicine. And the future? We're moving toward embodied AI, systems that learn not just from data, but from interacting with a physical environment. A robot that learns to walk by trying, failing, simulating, and improving, each trial guided by a physics engine that tells it exactly how its body should move. No trial and error in the real world. All learning happens in a differentiable simulation, then transferred to reality through careful calibration. This isn't just about smarter AI. It's about more truthful AI, systems that don't hallucinate physics, don't violate conservation laws, don't generate impossible outcomes. They don't just mimic the world. They understand it. We're no longer training AI to imitate reality. We're teaching it to reason about it, using math, physics, and gradients as its language. The next generation of artificial intelligence isn't just smarter. It's realer. And that changes everything.